Hello, this is Professor David Clough, and what this screencast represents is the first of three workshops related to using Python for typical chemical engineering problem solving and calculations. We're assuming for this first workshop that you have little to no familiarity with Python. You may have had some experience with the MATLAB package in the past, but you are new to Python. So that is our approach here. You can see the outline here. We start with introducing the integrated development environment that we're using, and then using what's called the IPython console for one-line calculations. And then we introduce some elements of the Python language that you can see here, down to creating simple plots and getting help. Finally, we have topics related to input-output, creating plots, creating user-defined functions, and understanding the program structure in Python, and finally, arrays and matrix operations. You will also find that there are similar workshops, a set of 3 for MATLAB, and also for the use of the Excel spreadsheet and VBA programming language. And all 3 of the sets follow the exact same pattern. And when it comes to the chemical engineering examples, they are identical. So we'll get started here. And take a look first at the integrated development environment that we have chosen for these Python workshops. There are several of these, and there are places that you will see them. We've chosen one here, which is called the Spyder IDE. It is particularly designed for engineering and scientific computations, and it has a look and feel which is similar to MATLAB. You of course can use any other IDE, but you will have to adapt that to the Spyder illustrations we use here. And then once we get past that and we're just involved with Spyder, with Python programming, you'll find it easier to move forward from there. But we recommend that you install Spyder, and the easiest way to do that is via the Anaconda package. And we show here where you can obtain that on the internet. And the Anaconda package includes numerous open source software packages, and among them you will find Spyder, and the icon command is shown here. And you can launch it, and then after you have launched it, you'll find a separate command button in Windows, and if you want, you can transfer that to your display or down to your taskbar. The versions of Spyder and versions of Python are a moving target. They're being updated regularly, and so you can go on the Anaconda interface and update these, and you will generally get messages in using Spyder when an update is available, and it will provide the command instructions that you can use to do that. So when we launch the Spyder IDE, this is what the window looks like. And what you will find here is that I switch back and forth frequently between these slide images, and if I Alt-Tab over to the actual Spyder window, and I will be going back and forth frequently. You will have a PDF of the PowerPoint slides that you can refer to later on, and you can also watch this and see how I go back and forth. What I do suggest that you do is, as I have here, that you have the Spyder window open so that as I go through exercises, you do them along with me. Later on in the subsequent parts of this workshop, you will find some longer code files that we've also made available to you, and you can open these files within Spyder, and that will save you having to type in longer segments of code. Okay? So going back to the PowerPoint slides, I'll just point out the features of the Spyder window, and that is down here there is something called the IPython console window, and that is similar to the command window in MATLAB. And then we have an Explorer window which has several tabs, and this can be set up similar to the workspace window in MATLAB. And then over here we have an editor window where, as we begin to develop longer programs, we build them in the editor similar to what you would do in MATLAB. Along the top here we have editor command buttons and then menu commands. Over on the right we have the folder path where you will keep your files. And then this Explorer window includes something called the Variable Explorer, which is like the workspace in MATLAB, but it also includes a plots tab where you can look at any plots that you create. And that is a little bit different than the MATLAB personality. So what we're going to do here is we're going to just do some very simple exercises over in the Python, the Spyder window. And I'm going to do it down here in the lower right in the IPython interface. And I'm just going to do some very simple arithmetic calculations, and then we'll summarize back on a slide what we have seen. So I'm just putting in here 55 minus 32 by 2, and I hit enter, and it uses an out designation to give me an answer of 39, 55 minus 16. And of course, what you'll notice here is that the division has taken place before the subtraction, which is what you would expect. And then I can try another where I do 12 by 3 times 2, and the answer is 8. And what you can see is happening here is that the operations of division and multiplication, which are at the same level of priority, are handled left to right. So you have 12 by 3 giving 4 times 2 giving 8. And then we have additional operators which are specific to Python. And so the double slash is integer division. So what it says is how many times does 5 go into 12? And in terms of integers, it's twice, because you get 10 with a remainder of 2. And then we have another operator where I do 12 and percentage sign 7, and that gives an answer 5. The percentage sign is the modulus operator, where what it does is it divides 7 into 12 integer-wise and gets 1, and then has a remainder of 5. So there's a modulus operator, which is the percent sign. You can actually use the modulus operator with numbers with decimal fractions. That turns out to be pretty tricky. And if you ever want, I'm not going over the details of that here, but those details are available in references and in help, and we'll provide you with some references and help information as we go along. The other thing to be aware of is I'm going to go 2 double asterisk 3 double asterisk 2, and the answer here is 512. And the difference here, and it's a difference to other programming languages such as MATLAB and VBA and Excel, is that Python does repeated exponentiation right to left and not left to right. So it does 3 squared and gets 9, and then 2 does 2 to the 9 power, which gives 512. So repeated exponentiation is done right to left. So let's pop over to a slide and summarize that. This shows you what exercises we did on the left, and then on the right it shows you the different operators that we illustrated, and then it shows the priority or precedence of these operators, and it's typical precedence with exponentiation at the top, negation, then the various multiply, divide, modulus operators, and finally plus minus. And you can see the comment that evaluation is left to right with items of the same precedence, except for repeated exponentiation. There's a comment down here on the lower left that I'll illustrate back over here, and that is that if I hit the up arrow, this is similar to MATLAB, I get the previous command. And then, for instance, I could come in and edit that and hit enter, and I could get a different answer, okay? And you are actually able to go back several lines of code and make a change and edit it and regenerate the answer. So you can use the up arrow to go back through the history and pick up repeated commands. That is particularly useful if you're using a longer expression and you hit enter and then you realize you've made a mistake, but it's a minor mistake. So you can use the up arrow to bring that back up and to make a correction, okay? So the next thing that I want to talk about is assignment. And here we're introducing the common use of variables. So I can, for instance, hit A equals 5, and it assigns the value of 5 to A. And if we have the variable explorer up here, you'll notice that it shows that variable. The type it has assumed is an integer variable with just one number stored, and that number is 5. If I use instead a capital A, we see that that is stored as a separate variable. So it is case sensitive in Python as it is in MATLAB, but as it is not in VBA. So here we have assigned a different value to capital A, and then finally, and again, it's taken as an integer value, and then I use B is equal to 6.0, and that stores B, and it gives the designation of type being float, which means that it is storing it as a decimal quantity, all right, with fractions, decimal fractions. So there are other data types in Python that we use at times. I'll illustrate these here. One is, if I can do test equals true, and true is a reserved value in constant value in Python, as is false. And you'll notice it has stored true test, and the type of variable is bool, which stands for Boolean or logical variable. And then another is Cx is equal to 24 minus 3j. And that's stored as a complex variable with a real and an imaginary part shown there. And then finally, I set switch equal to a string, a text string enclosed in apostrophes, and it's noted as a str or string type, and its value is on. Another thing I'll point out here, I'll pop the up arrow, and I'm going to come back here, and I'm going to replace this with quotation marks. And that also works. So we can delimit strings either with apostrophes or with quotation marks. And you can see that that continues up here, and it is now set to the value of off. All right. So that is something on that. And if I pop over to our slides, you'll see that this is summarized on this slide. I don't need to go over this because we've already done it over in the Spyder window. So let's come back and continue this. I'm down in the lower right. I'm going to make a calculation of a favorite number of mine, which is the golden ratio. So I'm going to put SQRT of 5 minus 1, the quantity in parentheses, right, divided by 2. And we get an error. And now we're starting to introduce limitations which are particular to Python. Python does not have a built-in function for square root. Native to it, like you would find in MATLAB or in VBA. So we need some help here. So we bring in a module called the math module. And then let me go back a couple here, and I edit that, and I put in math.sqrt and put enter, and I get the golden ratio. And so here I am using a set of functions which is available in what is called the math module. And what you'll find in Python is that we import various modules to help us with our numerical calculations. And math is one of them. So let's go back to the slide and take a look at that. And so here is where I illustrated that SQRT doesn't work. And in fact, there are very few math functions directly available in Python. 2 of them are ABS for absolute value and round for rounding. And here is where I imported the math module and then proceeded SQRT with math dot, and I was able to do the calculation. I note here over on the right that the math module functions only operate on single quantities and not arrays. Later, we will use a module called NumPy that has functions that do operate on arrays, and you'll see that shortly. But down here, there are some typical functions and constants that are available with the math module, typical trigonometric, exponential, and log, hyperbolics, and constants built in such as pi and the Naperian E. And they all have to be referenced with math.name, okay? So let's move on from that and go back over and illustrate relational and logical operators. So one thing I'm going to do is I'm going to come up here with remove all variables, and I'm going to clear the Variable Explorer workspace. And it notes that I've done so down in the IPython window. And then I'm just going to set some values, A equals 12, semicolon, B equals 8. And you'll notice we can string together two commands or more by separating them with the semicolon. There's a personality for you. C equals -3, semicolon, and D equals -5. Okay, and now these show up here in the Variable Explorer. And then I'm going to create a logical expression, not A less than B and C greater than D. All right. So if we take a look at this, let's look at, is A less than B? No, so that's false. Is C greater than D? Well, on the number line, it is, so that's true. But then we have a not operator which operates on that false here, and makes it true. So we end up with true, and the result should be true, and it is. So let's review that and on the slide and give you the rest of the operators so that you can see them. So the operators over here are shown a logical equal. Numerical equal is double equals, which if two numbers are exactly equal will yield true. Not equal to, in this case, is exclamation point equal. Your greater than, less than, and greater than, equal to, less than, or equal to are familiar. And the logical operators are not, and or, and these are in order of precedence. So not will be evaluated before and, which will be evaluated before or. And then if there are any other distinctions, it will be left to right. So this shows the logic we applied to obtain our result. Okay, so let's pop back over and introduce a new topic here, and that is add some complexity to Python in general, but we can simplify it reasonably well for our numerical calculations for engineering and scientific problem solving. That is how that Python has different ways to describe collections of data. So I'm going to assign one which is called my list, and I am going to put that in brackets, and I'm going to put 2, false, and I'll just put a string in, oats, in apostrophes, and 0.618. Okay, so I have made a list here. What says it's a list is the brackets, and you'll notice that a list allows you to have different types as part of the list. So we've got an integer, we've got a Boolean, we've got a string, and we've got a numerical, all right? Now, we can describe a different type of list, which I'm going to edit this, and that is called a tuple. And we replace the brackets with parentheses. And now you'll notice it's listed up here and it's shown with parentheses. Now, the difference between those two is that with the list, we can actually modify or change the individual entries in the list, all right? But with a tuple, the elements are what are called immutable. In other words, we cannot change them. The only way we can actually change one item is by reassigning the entire tuple with one item changed. So that's the difference between those two. And you'll notice they both allow us to store different types. And as a result, they turn out to be not that well suited to numerical calculations. And then we have a third one, all right, which again, I'm going to edit from the tuple, and it is called a set, all right? And we designate it by in this way, all right? And then that gets automatically called a set, and it allows us to carry out the kind of things associated with sets, such as union, intersection, and so forth. And it uses braces, whereas tuples use parentheses and lists use brackets, all right? So it may be new to you, but you'll get used to it as you go along in time. And the final one is pretty specialized, so I'm going to create it with a variable called 14ers, and this is again going to be in braces. So I will create the first item called Albert, and then with a colon I will put in 4401, all right? And then I will separate that with a common, and I will put in massive, then another colon, and I will put 4398. I'll stop that there so that it will fit on the screen for you, and end that with brace. And here, 14ers is called a dictionary, where we've got a word and then we've got essentially a definition of the word, in which case it is the elevation of the mountain in meters, okay? So that is called a dictionary, and you might find any of these used in examples, but the more important collection of data for Python for us is called an array, and we will get to that as we look at our subsequent slides. Let's pop back and review the slide for this. This is just gives you the examples that we've used and the fact that you use, the fact that you use brackets, parentheses, and then braces for the other two. And it mentions here what we have for an array, and the main consideration there is that the array contains a single type, and it's accessed by integer subscripts, and the array type is provided by the NumPy module. It is not inherent to Python. So this we'll be using extensively in our numerical methods and applied statistics calculations, and you'll see that coming along. Okay? So the next thing I want to pop back over and get into looking at elements of lists, etc. So I'm going to put in my list, and then in brackets I'm going to put 0 and hit enter, and I get 2. Now you'll notice that up above that 2 is the first element of my list, and that has an index or subscript 0. So what you're noticing here is that Python's subscripts of collections and arrays have an origin at 0. So the first element is indexed 0, and so forth and so on. For instance, here, if I do my tuple, whoops, let's spell it right, 3, that is 0.618, and you'll see that that is actually the fourth element, but if you start counting at 0, it's index 3. So just coming back to the slides to review that, you see that for indexing, they are 0-based and not 1-based, as you will find in MATLAB. And then Excel's VBA is actually 0-based by default, but you can change it over to 1-based using the option base 1 declaration. That's just a detail along the side. Okay, so let's come back over. And what we're going to do is introduce the concept of arrays. And in order to do that, we need to import the NumPy module. And what we do here is we use an as clause, NP, and you can call that anything, but it's typically called NP. And that is so that when we use something in the NumPy module and have to precede it by a designation, we don't have to type NumPy every time. We can just type NP. So, for example, here I can set x equal to np.array, and it provides me a little bit of help here. And then in brackets, I'm going to create a list inside the parentheses. So it's going to be 2.3 minus 4, 23.45, comma, 5.6, comma, and minus 14.77, just a collection of random numbers. And then I terminate it with a right parenthesis and hit enter. And now down here in the variable window, I will see that X is now called an array of float 64. Now what float 64 is a particular way of storing decimal numbers in 64 binary digits. And we're not going to go into the details on that, but we'll show you the source in a little bit. And then I'm going to come along and I'm going to come down here and create, and you'll notice this is an array now. That's the type, and it's shown as having 5 elements and then a comma, which means it would allow for a number of columns index, 5 being the number of rows. So it puts the comma in there, y equals np.array, and then we will use a tuple instead. And I will just use 1, 2, 3, 4, and 5. And you'll notice it's a tuple because it's surrounded by parentheses. And So let me scroll this down. And you'll notice that the type here is integer. It's stored in 32 bits, all right, which is a standard integer. And it's denoted that because all of the elements, all right, of the list are integers. When I did the assignment up here, you'll notice that one of the elements was entered without a decimal point, but since there were others with decimal point, it automatically elevated that into a floating point number. All right, so that's what we see there. And let's summarize that on a slide. So you can see our import and then our assignments here. And you can create an array from either a list or a tuple. And then this is how it's denoted in the variable explorer. And float 64 that indicates that it's stored in 64 bits, 8 bytes, according to an IEEE standard layout of the bits. And you may have been exposed to that in the past somewhere, but I provide an internet reference here for it. And then int 32 is as shown. And I have the same comment here about the 5 comma, in that it allows for a second set of indices, a second dimension to essentially represent matrices. Okay, so let's come back to our Spyder window and do a little bit of work with what we have here. I'm just going to come down here and type X. And again, when you're doing indexing, always use brackets. And it shows 23.45 for X. And that's 2. And you'll notice that for X up here, first item is 0, second is 1, third is 2, and we get 23.45. There are some additional things that you can do are similar to index operations in MATLAB, maybe not quite the same. And here I'm going to do Y1:3. Whoops, let's make that a bracket. I look at that and it says it should be items 1 through 3 of the Y. And this would be 2, 3, and 4 because index 1 would be the second one. So if I hit that, you'll notice that it only gives me the 2 and the 3. So there's an idiosyncrasy. And that is when you use the colon for a range of indices, it does not include the last item. All right? And that's just something that we've got in the slides and I'm illustrating to you. And eventually you'll need to get used to it. All right. The second is that we'll try X bracket 1 colon and just that. And that gives me, for X, it gives me, starting with -4, it gives me the rest of the array. And so that the colon means go to the end of the array, and it leaves off the first element, which is the 0 index. And then another one that I could do is Y bracket colon 3 right bracket, and that gives me 1, 2, 3. So again, here we're encountering an idiosyncrasy similar to what we saw up here. Is that for Y, it's given me 1, 2, 3. It's given me indexes 0, 1, and 2, but not index 3 as you might expect here. So it's up to but not including the final index as it was up here, all right? So again, we'll just pop over and summarize that on this slide. The important element here, apart from the examples, is this middle paragraph, and that explains zero-based indexing with ranges 1 through 3. We would expect the second through the fourth, not so We apologize. And so I colon j extracts zero-based I minus 1th element up to but not including the j minus 1th element. All right? And then this explains similar with the colon used either after or before an index. Okay? So let's pop back over and let's move on. Now, we can talk here about array operations. So for instance, if I do 2.3 times y, all right, what it does is it takes and multiplies 2.3 by every element of the array. And that's probably what you'd expect. It's scalar multiplication, all right? And then if I do x times y, that is an array operation. It does item by item multiplication. So 1 times 2.3, 2 times minus 4, 3 times 23.45, etc. So it's an array operation. And if you wanted to do that in MATLAB, it would get you involved in using the dot operator before the asterisk. But this is what happens naturally here. And if we want to start doing calculations like matrix calculations, vector matrix calculations, that's not done this way, and we'll see that later on. Also, we can take a built-in function like np sqrt, and then we can do that for the y array, and it gives us the square roots of each element of the array. Okay? So summarizing that on a slide, we show the illustrations here, and we note that NumPy's built-in functions work with arrays, but the math module's functions do not. For that reason, we tend to use the NP functions and not use the math functions. And you can carry out array operations. You cannot carry out array operations with lists or with tuples. And we end up using NumPy more frequently than math. All right. And you'll find that out. I had a list up here, which is called my list. And if I end up saying something like 2.3 times my list, it doesn't like it. All right. You can't do that. Okay. So let's move on from there. And let's consider creating a two-dimensional array. So the first thing I'm going to do is create a two-dimensional list, and I'll start that with a capital X equal to, and then I'll use a bracket for a list, and another bracket, and then 1, 2, 3, and then a comma separator and another bracket. It's like a list within a list. 4, 5, 6, another comma, 7, 8, 9, and then a terminating bracket. So these are 3 lists within a list, and it created that, and you'll notice up here it's called a list. All right. And then what I'm going to do is I'm going to convert this to an array. So I'm going to say capital X is equal to NP array of capital X. So I'm going to lose X as a list and create it as an array. And now capital X is shown here as an array. And if I need to see a little bit more, what I can do is double click that X, and it's sort of like looking at the matrix display in MATLAB, where I can see how that's laid out with respect to row and column indices. Okay, so that is what I have there, and I do have the ability to carry out array operations on a two-dimensional array. So I can do, for instance, np.log10 of capital X, and there it applies the common logarithm to each element of the X array. All right, so I've got that, and again, following our progress, that's illustrated on slide 13 here, and you can see that it summarizes the operations that we've carried out. Okay, so we're going to move on from that now, coming back over, and we're going to import another module which is very commonly used, and it's called matplotlib. It's for creating plots. So we're going to import matplotlib.pyplot, which is a submodule within matplotlib, and I'm going to give it a shortened an abbreviation PLT, so I don't have to type that every time. And PLT is what is typically used. And so we'll start. I'm going to clear my variables up here, and then we're going to start by creating an array, np.array of a list, which is 1.5, 2.6, 4.3, 6.7, and 9.9. There's your list terminator array, and it lost my connection to NumPy when I cleared everything. So let us go back. And then let me go up twice and try it again, and it's happy. Okay, so we just learned something there. And as you'll find out later, we do most of our work over here in the editor window for these kinds of things, and not in the IPython command window, but we'll stick here for now. And then we're going y equals np array, and once again, we'll create some numbers here, 25.7, comma, 12.9, comma, 17.8, minus 3.4, and 7.7. Terminate the list, terminate the array function, and hit enter. And now it shows my two arrays up here. And then what I am going to do is I'm going to make sure I've got this going here. I'm going to import matplotlib.pyplot as PLT. Make sure I have that. Might have been wiped out when I cleared the variable explorer. So, and then what I will do is I will do plt.scatter for a scatter plot of x comma y, and I will hit enter. And it gives me a hint that in order to see the plot, I need to come up here to the plot tab in the Explorer window, and there is the plot that I've created. Nothing very special, but it shows how we can import that module and create a plot. Now, if we want to start adding features to the plot, like titles and grid lines, etc., then we really need to be working over here in the editor window, and we're going to be going there now. Okay, so let's come back over, and this shows what we did in creating that simple plot, and where you can look at it in the variable in the Explorer window under the Plots tab. Okay. So now what we're going to do is create a little more sophisticated set of code, and that we are going to do over here in the editor window. Now it has some initial code there that I'm just going to delete. So we have an empty editor window. You'll notice there's a tab here. It says untitled0.py. .py is the extension for a text file that contains Python code. So what we will do here is I'll take the time to enter a few statements to create a little more sophisticated plot, and that will get us into the use of the editor window. And you can certainly type in with me, pause as needed. So we'll start with our import numpy as np, and then we'll do the other one, import matplotlib.py plot as plt, okay? And then we're going to create an X array, np.array of a list, which is 1.5, 2.6, 4.3, 6.7, and 9.9, similar to what we had before. And then we're going to create two different Y arrays called Y1 for the first one, np.array, open that list. You'll notice when I open the list, it provides for me the right bracket automatically. You keep that in mind. We'll start with 25.7, comma, 12.9, 17.6, minus 3.4, and 7.7. And then we'll do a Y2 array. And those numbers will be 20.2, 15.3, 10.6, 3.4, and 15.2. Just sort of numbers picked out of a hat. So now we have two arrays, and we've got two Y arrays and an X value. So now we're going to do a PLT dot plot, not scatter, but plot, which is asking for a line plot. And I'm going to plot Y1 against X. That'd be X comma Y1. Then I'm going to put in some options. Color option is going to be equal to the letter K in apostrophes, and that stands for black. I'll show you those codes later. And then I'm going to do a marker item, and that is going to be S, which stands for square markers. And then I'm going to do a label argument, and that's for use in a legend, and I'm going to call it Y1. So that's what I have for that, okay? And then we're going to add to the plot, and this is where in MATLAB you might have had to use the hold on command. It's not required here. Y2, and again, color will be equal to, it's going to use the same color, black, for black and white. We will marker equals D for diamond, and then we will do line style equals, and again in parentheses, 2 dashes, comma. Just going to come down to the next line with a return. Since we're in the middle of a function with arguments, we can do that. It's a little different when we have like arithmetic expressions. We'll cover that later, how to do continuation with that. And then we will do label equals y2, and we've got that. It's not a bad idea as we are going along doing this to save our files so that if something went wrong somehow, you wouldn't lose it and have to start over. So this is called untitled0.py. So I'm going to come up to File and do a Save As, which we note is Control-Shift-S. And give me a moment to find a good folder for this. And for the file name, I'll call it First Plot. And it asked me if I want to replace the one that's already there, and I said yes. And then I'll add a few other statements here. PLT grid, no arguments needed for that at this point. PLT.xLabel, and I'll just put in X. PLT.yLabel, and I'll put in Y. And PLT.title, and I will put in 2 Y arrays versus X. So there. Now, one thing you'll notice up here is the first plot tab now has an asterisk by it, and we can run this program okay, but what the asterisk means is that we haven't saved it lately. So if we hit save, the asterisk will go away, and it's just a reminder up there to save your work. Oh, and we can add another command here, and that's legend, which will take advantage of these labels that we created up here, okay? And so having this, we can see if we get lucky and we run this code, and there is the array, the plot that has been created, and you can see that we've got all the elements there that we put together for it. And so having this code in place, we can now start to explore some other features of the editor that will be useful for you to know about. So let's just come back to our slides. There is the code that we created. We saved it as firstplot.y. It adds the py automatically for Python. And then we ran it with either the F5 key or the run file play button up on the toolbar. So coming back over, the play button is up here. There's also a run menu item that we can choose something from, and then you can use the F5 key to run the code. Okay, so that's what we've got there. Now, what we want to do now is explore some features of the editor that relate to debugging. So what I'm going to do here is I'm just going to remove the final parentheses on that assignment statement for X, and you'll notice immediately we get an ugly red dot out there with X in it, and if we hover on it, it comes up with a diagnostic which is pretty useful. It says the open parenthesis was never closed. So it's not going to let us run the code till we correct that. So once I put in that parenthesis, it's happy again. All right. Another thing, I can come down here, for instance, and with the first plot command, instead of X, I can put in Z or Z. And as soon as I do that, it complains and it says you've used an undefined name Z. All right. So coming back and correcting that, that red goes away. Another thing that can happen here, at least temporarily, or maybe even more so, is that if I import another module like the math module, it gives me not an X, but it gives me a warning. And the warning says you imported math, but you never used it. All right. And so that'll always show up as you're starting to write your code, eventually should disappear. But since we're not using the math module, I will get rid of that. Okay. So let's move on. You notice every time I make these changes, it encourages me to save it again. Let's look back at our slides. There is the plot that we created, all right, which is typical of Python plots, and later on we'll get into a lot more features of those. And then this illustrates the changes that we made that caused the X errors, all right? And that is what we've got there. And then we get these warnings that came up when I put in the math. So these are diagnostics that you get before you even run the code. The next thing that you want to know is how you can go about tracking errors that occur in the code that are execution errors. And the best way to do this is to single step the code, where I'm going to bring the variable explorer over here and let me clear it out. And then we're going to come in here and we're going to go up and use this button, which is debug the file, or Control F5. So if I click that, it starts execution and it puts a blue right pointing arrow by the first line of code. And then what I can do is I can single step the code. There's a button up there for that, run current line, which is also Control F10. So if I do that, it does the first, it does the next, and it does the next. And as it goes by the lines, the values of my variables show up in the variable explorer. All right. Now, if at some point in time I've seen what I need to see, I found an error or whatever, I can use the big square stop button up here, and that stops the stepwise debugging for me. All right. Now, another thing that I can do is if I start debugging and do Control F10 for a few lines, then I can hit F5 and it will complete the execution, but it'll still leave the marker on that particular line. Now, if I want to bail completely, I use the Stop Debugging button. All right. And another thing that I can do, and we do this quite often in MATLAB and in VBA, is that I can, if I don't want to single step through a whole bunch of code, I can come to the left of an item and click and put a red dot there, which is a breakpoint. And then if I go into debug mode, it will run the code to that line and stop. All right. So you'll notice it did not stop at the first point and let me single step. If I wanted to do that, I'd have to put a breakpoint up here. Let me bail out of this. And then I would do that, and it would start, and it would go through that first one and come to the second one. Now, if I want to get rid of any one of the breakpoints, I can click on it, and it will go away, and I can stop debugging. So that's a little bit on debugging, and you'll see that more examples of that as we go on through the workshop. Coming back over to our slides. And so this shows going and starting with Control F5 or the command or off of the debug menu, and then it's single stepping with either the command button here or Control F10. All right, and so I can do that, and I can step down through the code and look for errors. And this shows some of the examples that we went through in terms of stopping the debugger, continuing execution, putting in a breakpoint, and in this case, there's a way to clear all the breakpoints in the debug menu if you have more than one, or you can click each one, click the red dot, and it will disappear. Okay? So we're almost to a point where we're going to take a little break here, but let us continue. So the next thing I want to cover is that it's very useful with your code, both for others and for you to have, if you come back to it some point later, to add comments. So we'll just show how to do that. You do that by starting with the hash or number sign, a little different from the % in MATLAB or the apostrophe in VBA. And so I can put in a comment, something like create arrays for plotting here. So I can do that. And then down here, I could come in and put in a comment that says, plot the Y arrays. Whoops, let's spell it right. Versus X. And then I can also add, as with the other languages, I can add a grid as a comment to the end of a statement to provide some explanation and so forth. All right. So adding comments is good. You notice here they show up in a little bit of a light gray, and that is okay. All right. And so the next thing that I'll point out to you is that we can create a new file in the editor. You can have multiple files open just as you can with the MATLAB editor. So I can create a new file up here with the leftmost command button, and it gives me that, and it puts in some standard heading here, and it's got a comment at the top about the coding font, and then it has some comments between triple quotation marks, and this is something that is called a docustring, all right, and it can be used as part of the help facility when we get into programming further. For the moment, we take a look at that, and we tend to delete all that as we get started. And then you can do the save as we did before, save as, and you can put in a name like my new file, and it creates a name for that. And then you can switch back and forth between these two, right? And you may have many, all right, as you're building more sophisticated programs. So that's a little bit on that. And then we can, when we're done with the file, we can just exit out, and it removes from that and the other one, and then it gives us a blank file with the standard header. So that's what we have there. We've noted before, you can clear variables over here in the variable window, and let's pop over and cover a little bit of that with our slides, and then we'll talk a little bit about help and take a break. So here, this shows adding comments, and there are a couple more added to what I did. And that you do it with the hash or number sign. And then just a little sermon about comments being useful and recommended. If you're going to submit code for review to supervisor or to an instructor, I think it's likely that they would expect comments to be there. Okay. And then a little bit here on creating a new file with a docustring between the triple quotes. And docustring we may find as we create functions to do things like solve equations, and then save as with a new file name. All right. And then finally, the idea of the asterisk being a reminder that you need to save the file, and closing it with the X on the tab. And as variables accumulate, typically you over in that Explorer window, you clear or remove all variables. Okay. Now, a couple more things I want to illustrate first, coming back over, and that is that there is a settings command up here for Spyder, and it provides some different ways to present Spyder. There are a number of highlighting themes that you've got here. And for instance, you can have the entire background being black with the text being sort of fluorescent, if you like that kind of a presentation. One thing that I have done here is I increased the font size of the plain text. And the reason that I did this for the workshop is that it makes it easier for you to see it in the screencast. So you've got some different things that you can do here in your preferences. And I'm not going to go over all of them, but I just want to make sure that you know that all of those are there. Okay? So we've got that. Now, at this point, we just want to review what the help facilities are that you have available to you. So if I'm down here in the console, let me just say I do x equals 3, and then I type print, and then it automatically gives me a tooltip as I'm typing in the print function, which gives me a little bit of an idea of what is the print function. All right. So then if I do X and hit enter, it displays 3. So you get some of that. If I bring back, let me bring back up first plot. And then if I hover on a command like plot, it will give me some help for that. And then if I click anywhere in here, it gives me over in the help window, it gives me a fair amount of information here on using that particular command. So if we know what command that we're interested in, right, then we, like grid, we can get information on it. And then if we click in here, we can get that. Another way to handle that is that if I click in here and do a Control I for information, it will give me help over on the right. It turns out that there is a help window up here for Spyder, but that's primarily for the use of help with the Spyder interface and to the IPython console down here. It used to be a long time back that they had additional items here that provided help, for instance, for the NumPy module and for the other modules of use. and for Python itself. But at some point in time, for whatever reason, with updates to the Spyder editor, to the Spyder interface, those disappeared. Okay? So if we come back over to our slides to finish this part up, this just gives you an idea of the Spyder settings with the little wrench at the top. And you'll notice that the font size here is 10, and I changed it to 12. Okay? And then you've got different flavors of help, and this is what you get when you hover on something, and then you can get the additional help in the help window, in the Explorer window to the upper right. I mentioned that the Spyder help window is not really that helpful to us. And then we go beyond that now, and we go to the internet. And for instance, we've got a link here for getting documentation on Python itself. And so when you do that, you end up getting this in your browser, and you've got things like language reference, library reference, etc. On Python itself. So that gives you that. And then we come along and you end up getting like specific manuals for NumPy. Another module we use frequently later on is called SciPy. And then there's a user's guide to Matplotlib. So you can do that. And I won't bring them up for you to see, but I believe you'll be able to click or control click on these links, and they will take you there. And then, or you can search for them. And then another way, which is pretty common, is to just go to Google or whatever and put in a question. In this case, I've illustrated how do I compute a dot product in Python, and it gives me an idea of how to do it with the numpy dot method. And then finally, down here, you can have help on using Spyder itself by going to this particular location. Okay, so we're in the next part of this workshop. We're going to move on, and we're going to deal with input, output, and with a lot of more sophisticated plotting. And so we'll do that, but at the moment, we're going to take a little break, and you can take a break too at this point. Of course, with the videos, you can stop and start whenever you want, but it's time for me to take a break. Okay, so that's it for right now.